So, welcome to my talk. So, first a disclaimer. So, although it says on the slide that this presentation has been given at the Lorenz Center on the 9th of August in 2022, this is a re-recording of this presentation. So, I will go over the slides that I have presented at the meeting Stability and Fluctuations in Complex Ecological Systems. Because although the talk was recorded at the Lorenz Center, unfortunately, they would not give me permission to post my own talk on my YouTube channel, so that's why I'm re-recording the talk. This means that what I'm saying is not exactly word for word, of course, what I have said at this meeting, but it will be sort of the same slides and the same topic. All right, so let's get started. So what is this talk about? I will go over critical transitions and early warning signs and resilience in sort of three parts. First part will be a basic introduction to critical transitions with the example, background, historical remarks and context, and the new results, so really the stuff that has been developed based upon the classical theoretical sort of framework. These results will be presented in part 2 and part 3. So first I will go over stochastic ODs, then stochastic PDs, and finally network dynamics. And for the third part in resilience, we are not as far as for early warning signs, and I will go over the basic classification that we have done for various concepts. So let's get started. Introduction to critical transitions. What are these things? So there's sort of in many time series and many data sets, you see a phenomenon that you somehow see drastic changes in time or upon parameter variation. And here I've just plotted 2 time series. And the goal is, okay, I see this time series and I sort of roughly, by sort of basic, the eyeball metric, I see that where there's this dashed red vertical line, a drastic change seems to happen in this time series. And this is a critical transition or a tipping point in some sense. And the mathematical questions that arise is first, how do we define these things? So what theory do we build critical transition or tipping point theory upon? The more sort of novel question is, can warning signs exist? So if you're on the left of this red dashed lines and you just are given the time series that's on the left side, then actually can you say how far away or if there's some transition upcoming? Then you want the dynamical mechanisms and scaling laws that somehow classify these transitions. And from a more sort of theoretical standpoint, you could also ask what techniques could you use to analyze them, and how sort of what variables should I measure in my system experimentally or from a sort of data perspective of crawling the huge data sets that are available to us now. So what measure should I plot to actually see these critical transitions and find the warning signs? All right, so I would say sort of the most successful, and in the end you will see probably the sort of the main or only framework that you can go with to model these critical transitions are bifurcations and phase transition theory. Bifurcations would be more the mathematical sort of notion, and phase transition would be a very much related notion that's more common sort of in the physical literature for multi-particle systems. So the classical bifurcation theory works for example, ODEs, but more general differential equations. So you have a given ordinary differential equation, u prime equal to f of u, and then you have some parameters, say v, and you vary the parameters, and then you see something's happening upon variation of parameters. So on the bottom left, if you take the sort of standard quadratic, that's the so-called fold or saddle node normal form, you vary the parameter v, you see that there is 2 steady states for v negative. The one on the top you can check quite easily by linearization is stable, the one on the bottom is unstable. You move your parameter, and eventually at v is equal to 0, you have a fold or saddle node bifurcation. And then if you go over that threshold, then after that bifurcation, there's no more steady states. So indeed, this could be a way how you could generate a trajectory that first sort of sits near a stable point, and then eventually if you vary a parameter, then it starts jumping. The same could happen at a transcritical bifurcation, where I've written the normal form on the lower right, so vu plus u squared, where you have sort of a crossing of branches or a sort of branch point, and then indeed you also have a stable branch and an unstable branch, and if you first follow the stable branch, then eventually it could happen that you are near an unstable branch and then you fly away. But this is not quite how critical transitions or tipping points are intended, because in some sense that's static. Here if you just had a fixed parameter set, then you would be in either situation. Either you would be in sort of stable case or you would be in the unstable case. What's sort of more reasonable is you make the parameters v dynamic. And once you do that, then you end up relatively quickly in this theory of fast-slow systems. So what are fast-slow systems? In the standard form, in the sort of base concept, you take an ordinary differential equation, you have a so-called fast variables u and slow variables v. The v variables are slow simply because there's a small parameter epsilon in front, which means that if f and g are order 1, then indeed for most of the time you anticipate that the v variables are evolving slowly in comparison to the u variables. You could also rescale time. If you do a standard time rescaling for epsilon small and positive, you can move the epsilon from the g in front of the g to in front of the du ds. And then you get sort of for epsilon positive an equivalent formulation of a fast-slow system. Roughly speaking, you can think of the easiest or maybe even most important class of fast-slow systems of those where there's a parameter that's slowly driven. Yeah? And then you see where this is going, because if you have a slowly driven parameter, then you might sort of generate these jumps over bifurcation points dynamically. And more on fast-slow systems, I studied in the US, so there are lots of sort of things you learn, and one thing is you once in a while should put in a commercial break on television at least. And there's a book that I have written that's called Multiple Timescale Dynamics from 2015, where this theory of these fast-slow systems is much more explained in detail. Alright, so fast-slow fold normal form. So what happens if I indeed make my parameter v dynamic and I sort of then look at the fold normal form again? Then if I start with a trajectory at the point sort of here, then I first see a fast transition, and this fast transition is actually pushing me up towards this upper branch of this object C0, which is the sort of null cline of the fast equation. So v is equal to minus u squared. This is attracting. So first I have this fast transition, but once I'm near it, then u prime is very close to 0. So then I effectively see finally the motion in v, and v is just increasing. So I'm slowly drifting along this object of dynamic, so in some sense, dynamic equilibria. I'm drifting along this object C0 that's also called the critical manifold. I'm drifting along it, and eventually I fall off, because if I go over the fold bifurcation point, the trajectory falls off and makes a huge jump. And if you see this in a time series, then indeed the time series looks sort of relatively stable for a long time, and then eventually it makes this jump when you go over the fold. So the time series is on the right. So as I said, this sort of set C0 for this fast-slow system, where you set all the fast variables equal to 0, that's called the critical manifold. You can define this in more generality. And there's a key regularity assumption that's called normal hyperbolicity, that says if you linearize with respect to the fast variables and you evaluate this linearization at a point P that lies on the critical manifold, and then you compute the spectrum of the resulting M cross M matrix, if all the spectrum is off the imaginary axis, then we say this critical manifold is normally hyperbolic. So then, well, you see that there's indeed normal hyperbolicity for most of our phase space above in the example. If you linearize the first equation, you get minus 2u, you plug in points, then you see only at 0, 0, so precisely at this fold point of the sort of fast subsystem when epsilon is equal to 0, only at this fold point normal hyperbolicity is lost, and it sort of tells you that these fast, slow dynamical systems, which are bringing you dynamically towards bifurcation points, they could be a good sort of object to study critical transitions or tipping points. And indeed, the points where you jump are these sort of points where you lose normal hyperbolicity. And indeed, if you go through the literature in depth, usually bifurcation theoretic and hyperbolicity concepts are the ones that are important. Sometimes they are hidden, but in the end, these are the concepts that really generate these sort of transition points. So, of course, this wasn't very realistic in a sense, because the time series I showed in the beginning, that should also be noisy, and most data sets you will find a noisy time series, because all the systems sort of in the real world, they indeed, if you measure them, there will be usually some sort of noise. So you have to upgrade this fast, slow fold normal form. And the simplest case you could upgrade this if you add additive white noise. So this W is a generalized stochastic process, which is the derivative of Brownian motion W. On the left, I've written this stochastic fast, slow fold normal form in the physics formulation. On the right, I've written this fast, slow fold normal form in the more mathematical E2 stochastic differential notation. And it's very important to note that there are actually three small quantities here. there's the sigma, which is the small noise. Usually you assume small noise, because if the noise that you put in is very large, then usually you didn't do the modeling very well. You would have to actually sort of, change your model and probably model the noise process as a variable. So noise, usually the unknown variable is sort of an unknown degree of freedom. So normally it's very natural to assume that these unknown things that you neglected are small. Then there's this slow drift, which is this sort of parameter drift, where you assume that there's a scale separation between how you vary the parameter and how you vary your state space variable, your main state space variable u. Also, this scale separation is very reasonable, because it's usually the case that these critical transitions are only happening in systems where you actually have some scale separation, because if you didn't have scale separations, they could just very sort of erratically and frequently happen, but you really see them as distinguished points normally in the time series or in the data. So, but now on the top left, you see the time series that this stochastic fast law system exhibits, and then you see on the right the projection of this time series in phase space, or the actual sort of trajectory in phase space, or the sample path of this stochastic ordinary differential equation. You see that this gets attracted still to the critical manifold, the deterministic object, it wiggles around it, and then it jumps off. And then you think, well, intuitively from a qualitative standpoint, the noise sigma is not very important, but indeed from a quantitative standpoint, from the viewpoint of early warning signs, it's extremely helpful. So let's suppose we are only looking at the red bit of the time series, and we are interested in whether there is an early warning sign for this upcoming fold point. Yeah. So you indeed see that if you plot this, and I plotted the variance with a sliding window technique of this time series on the right, you see already by sort of eyeballing it that the variance goes up when you come closer and closer to the fold point. You can actually prove this. So there's a sort of intuition that this comes from the fact that the variance increases because the linearization that deterministically pushes your trajectory back towards the critical manifold, that this linearization is minus 2u locally, but this linearization becomes smaller and smaller the closer and closer you come to the point of normal hyperbolicity, loss of normal hyperbolicity at u is equal to 0. And then, if you assume, and generically that's true, the noise generically at that point is not sort of depending upon the parameter distance to the critical transition. If it's then additive, like it's here, then indeed the noise fluctuations can increase because the deterministic pushing that pushes the trajectory towards the critical manifold reduces. So indeed, by the variance growth, you indeed see a warning sign for the upcoming transition. Yeah, so this is very nice. So you can somehow use the noise to probe the system, and by probing the system with noise, you indeed find that there are warning signs for these transitions. Yeah. Very good. So of course, as I said, this is sort of a super mini survey of lots of theory that has been developed over at least, several decades. So this history is not a history that's complete, and it has to be read always like that the sort of year on the left, for example, the 1940s, is sort of at least since the 1940s, or at least since the 1950s. So first there was autonomous bifurcation theory that has been developed sort of concurrently with phase transition theory in physics. Then in the 1950s, people realized there's this sort of scaling law behavior when you approach a sort of bifurcation or phase transition point, and critical slowing down was discovered, that indeed the system sort of slows down after you perturb it in recovering because you are getting less and less stable. And then in the 1980s, it was realized that these things could be used as warning signs if you approach a bifurcation point. And then in the 1990s, more sort of stuff was done on non-autonomous bifurcation theory, which is still sort of under development. And then in the 1990s, sort of concurrently, you could even lump them together and say there was also stochastic bifurcation theory, so systems that are stochastically forced. And then in the 2000s, there was sort of this rediscovery, let's say, or popularization and application of warning sign theory to data and to several examples that was pushed particularly in the community of ecology, community of climate science, and several others. And then in the 2010s, people realized, well, we need some sort of mathematical classification of warning signs. And I have been involved in this quite a lot, trying to write out a sort of more detailed theory that really quantifies and categorizes all these possible warning signs that you could see when you approach the bifurcation point. Yeah? And there's lots of papers, hundreds of papers in this subject, And if you're listening to this talk, I would sort of urge you to look into my papers and my books. I've tried to really be quite detailed in most of these papers with referencing, and you will find lots of reference and can trace the reference tree from these papers. All right, so thousands of citations needed, so within one talk I cannot give a complete accurate history of everything. All right, so now we can actually go a little bit to the history. So one little warning, there has been a sort of instance of rebranding or rediscovery in this area, like in probably many areas of science this happens, then this is no exception. So for example, in ecology, which is this community where I've been presenting this talk, quite often there's a paper by Carpenter and Brock that's cited where they sort of propose that there could be a warning sign by looking at the variance for critical transitions in ecology. But let me point out, for example, at least in as early as 1985 or even earlier potentially, there's a paper, for example, by Kurt Wiesenfeld that says noisy precursors of nonlinear instabilities, which exactly sort of proposes, you can look at the moments near bifurcation point, and then indeed you can use that as a warning sign or precursor for that bifurcation point. So the phenomenon and the idea has been around for quite a while. Yeah. So there's also sort of different types of tipping or critical transitions. For example, rate-induced tipping, which was sort of proposed by a couple of people at the beginning of the 2010s, and you see that while this is basically in the end reducing, if you look at it, there's a parameter that's ramped at a certain rate. But if it's a very small rate, then it's singular perturbation theory. If it's a larger rate, then it's basically, turns out, if you rewrite everything properly, it's non-autonomous or global bifurcation theory. So also rate-induced tipping is in some sense a more global or more sort of, special case of global non-autonomous or singularly perturbed bifurcations. So it's still a bifurcation-induced tipping. It's just more complicated or more complex because it's more global than bifurcations that are local, like the fold and the transcritical that I had shown you. Also, later on, we will get to the concept of resilience and also many resilience concepts. So what does stability globally actually mean? Also, these have been sort of rediscovered or rebranded. For example, there was this proposal of basin stability that you should measure the size or the volume of the basin of attraction to say something about global stability. But this has been, discovered before that maybe basin size is relevant. For example, there's this paper by Resch et al. On basin size evolution between dissipative and conservative limits, where they also measure the size of the basin. So this has been around for quite some time. And this is true for many of these things, so you have to be very careful in trying to sort of sort things out. And from a mathematical standpoint, I was particularly interested in trying to write out for some of these sort of discovered effects or phenomena that have been around in applications, a more detailed sort of consistent theory that you could write down and apply out of the box, like a little bit like a toolkit. All right, so let's come to this toolkit, and let's come to this toolkit for warning signs. So let's look at first the case of stochastic ordinary differential equations, and let's try to discover how we can develop such a toolkit. So here's the result. So in generic stochastic ordinary differential equations, so the noise is sufficiently generic, you have a sufficiently generic bifurcation conditions that are satisfied, and I'm covering all the bifurcations up to codimension 2, meaning that the v variables, which are the slow variables, will be two-dimensional. And then since I need up to codimension 2, I need 4 fast variables because some codimension 2 bifurcation appear only in 4-dimensional systems. So in total, this covers everything that's generic up to sort of 6 dimensions. And then you can actually figure out that if you look at the leading order covariance scaling when you approach the bifurcation point, so you generalize from the variance to the covariance, and you look at what's the leading order of the covariance matrix of your fast process as you're slowly drifting towards the local bifurcation point, then indeed you figure out that this can be completely categorized and mathematically classified what all these scaling laws are. So I'm approaching the bifurcation point from the stable branch. So V goes to the bifurcation point at 0 from the stable branch side. I assume that there's a certain noise level sigma, and then I can show that indeed for certain types of bifurcations there are certain scaling laws. So the variance grows like V to the minus 1/2 for a fold bifurcation. For a transcritical that I had shown before, it grows like V to the minus 1, and the same for a Hopf bifurcation and so on. So as you approach the bifurcation point, there's a growth of the covariance or the variance in the one-dimensional case. Of course, if you dynamically then jump over at some point when you are going away from the linearization regime, then it saturates. And then, of course, there's a saturation, but that saturation of the variance only happens very, very close to the actual transition point. So the thing that you actually measure in the time series is for a sort of very long time scale. You measure a certain scaling law, like the scaling law v to the minus 1/2 or this scaling law v to the minus 1, which you can simply measure from a log-log plot. Yeah? And these scaling laws can then serve as warning signs. So if you knew, at least from a sort of basic physical or ecological or biological standpoint, what the type of transition would be that you anticipate, for example, a hop or a fold, then you would know you would have to watch out for a scaling law like this. And then you can actually figure out how far you are away from the critical point, because here I assumed in this theorem that the critical point is at 0. So at v is equal to 0, the bifurcation happens. And if it doesn't happen at 0, then you basically have a scaling law that says v minus v critical to some power alpha. And then this scaling law can be used via standard log-log plots to figure out how far away you are from the critical transition. Of course, in an idealized setting, there are plenty of things where you can sort of cook up counterexamples, but these counterexamples then apply if the condition of this theorem are violated. So sometimes there's this unfortunate thing that I get this sort of request, well, why didn't you include this and this? Well, I said, well, the example and the counterexample, this is all in the back of the papers, but unfortunately, sometimes, particularly in some application areas, people don't read up to page 45 or 50 or so. So maybe I should have split that up into several papers, but yeah. So in principle, it's all in this Journal of Nonlinear Science paper from 2013, which is, I admit, quite long. So what's the proof for the mathematicians? A little bit of a remark, since this was a talk at an ecology conference that's more centered around sort of theoretical ecology, theoretical physics, and applied math. I will not go into the details of the proof, but the idea is that you are over this large time span where you are approaching the bifurcation point, you try to use linearization methods, and in particular, the Lyapunov equation appears, which is a key equation from control theory. You can actually figure out that you can solve this Lyapunov equation for all bifurcations up to codimension 2 for stochastic ODEs, and then you figure out that indeed this gives you the scaling law. And if you want to prove that is actually the leading scaling law, then you could either do a moment expansion and actually figure out that the higher order moments are small. In some sense, you can estimate it sort of term by term, or you can use martingale methods and Dupes inequality. It's a technique that was sort of pioneered by Berglund and Gens, and you can look it up in their book. That also would give you that indeed for up to codimension 2, the scaling laws can be calculated. Very good. So this is a relatively old result from 2013. And then the question was, well, what do you do with that result? I mean, you can apply it to many systems, but there are, of course, some systems where it doesn't apply. So while there's extensions, you can apply it to more complicated singularities. You can make it more robust by looking at it statistically and looking at time series and ROC curves. You can make the system heterogeneous. You can go to discrete time. You can change to bounded noise. You can assume that not the linear terms are leading, but the nonlinear terms are leading. But it turns out that this theory is incredibly robust and can be extended to these cases if you work a little bit quite naturally. So somehow, if you are in this finite dimensional setting of stochastic systems that are slowly driven, this is indeed an extremely robust approach. But there are, of course, cases which are not covered and where it's more complicated and where you need new theory. And one of the cases is stochastic partial differential equations, so SPDs. So now I will briefly talk about the results for warning signs for SPDs. So this is more complicated, of course. So let me go through the background a little bit. So I will mostly work on a domain, D, and it will be now space and time. So I have a partial differential equations, and the unknown I will denote by uxt. Quite often, but not always, I will be in sort of the case when this is scalar, but you can apply it to systems in principle. And the key class of PDEs that I want to look at on the deterministic level that later on I will augment with noise. And here V will be parameters for now. In the end, I will make a comment on how to maybe make V dynamic, but that's still under development. But let's look at first a case when V is sort of infinitesimally slowly varying. So it's extremely slow, like almost quasi-adiabatically, you would say in physics that this V is varying. And then let's look at this class of reaction diffusion equations. So A would be the Laplacian, you'd have a nonlinearity, and these reaction diffusion equations are sort of the closest thing in some sense that you could get to ordinary differential equations on the PDE level. They behave a little bit like nice evolution equations in Banach spaces, and there's many analogies between ODE theories and dynamical systems and PDE theories and dynamical systems if you sort of generalize to reaction diffusion equations. So this is the natural test case. And again, there's sort of the second commercial break. If you want to know more about the deterministic theory, you could look at my second book on PDE dynamics that appeared a couple of years ago, and there the sort of key class that's featured is reaction diffusion equations. All right, so let's look at the reaction diffusion equation case, but let's add some space-time stochastic process. So psi of x and t will be my noise, and then I have a reaction diffusion equation with noise. And what are the main reaction diffusion equations I'm motivated by? So these are particularly sort of these three, but there are others, of course, that would be interesting. The first one, it's basically a reaction diffusion equation where you have the heat equation plus a nonlinearity that's cubic. So basically bistable. So if you linearize, you see that u is equal to 0 and u is equal to 1 are locally asymptotically stable, and that u is equal to a is a steady state for the deterministic system, which is unstable. And then you add some noise onto it. The deterministic system has been studied a lot. In ecology, it would be a reaction diffusion equation with an Lie effect that didn't quite fit on the slide here. But in neuroscience, it would be the Nagumo equation. In material science or physics or phase transition theory, it would be the Allen-Kahn equation. Then in sort of normal form theory and parts of statistical physics, this would be the Real-Ginzburg-Landau equation. In quantum field theory, it would be the 5,4D model. And in chemistry, it would be the Schlögl model. All of this is basically the same equation. It's just different names and different branches. It's still sort of a bistable reaction diffusion equation. And now we are interested in this bistable reaction diffusion equation when we add some noise. The second important one is the Fischer Kbp equation, Fischer, Komrov, Petrovsky, Piskunov. And that equation has a quadratic nonlinearity. And that one means that there's sort of one unstable and one stable state. Locally asymptotically, and then you could also add noise on that. And the third model I'm very much motivated by, because I also did my PhD on it, is basically take the Nagumo equation and then couple it to an ODE, which is called the Fitsu-Nagumo equation, where you basically have another variable V that you can think of as an input current in neuroscience, and that's sort of mediated or controlled by a gating variable V, and this gating variable V is actually slow. So indeed, there is natural fast flow systems also in the PDE context. So it's a natural notion of fast flow systems also in the PDE context. So okay, let's look at now what we can do with these SPDEs and warning signs. So first of all, I need to explain what the noise is. So the noise is basically given by constructing first the spatial sort of structure for the noise, and this is done by picking sort of an operator Q. That's one option. So fix a Hilbert space, for example, L2 of our spatial domain. Let's fix an operator Q that's linear, symmetric, non-negative, and then look at its eigenbases and eigenvalues. Let's suppose it's orthogonal, and then you take an infinite chain of IID Brownian motions and you define a Q-Wiener process as a space-time process W that's spatially basically determined by the eigenvalues rho k and the eigenfunctions qk of my operator Q, and then this is basically forced. All of these modes qk are forced by independent Brownian motions. The derivative of this is again a generalized stochastic process, psi. Alright, so some remarks. You can show under reasonable condition this converges. For example, if the operator Q is trace class. So I will assume that for the rest of the talk, whenever I talk about SPDEs, I will talk about the simplest noise that I can sort of deal with mathematically, and that would be trace class. The interpretation of Q is, if you look at it carefully and you take the Brownian sort of Q-Wiener process and you evaluate the autocorrelation function, then you indeed see it's the normal autocorrelation function in time. So it's white in time, but colored in space. So in space, there's a spatial correlation. So Q is basically the spatial correlation operator. And the regularity is quite bad. So if you had Q that's, in this case, not trace class, but even if you had it trace class, then in many cases you cannot sort of get an actual true process, but you only get the generalized stochastic process if you differentiate the QV norm. So this makes some of the difficulty. Yeah? You get a very difficult process. So now let's consider these SPDEs and let's do dynamics with them. So let's take this SPDE with additive noise, where B is sort of thrown in for good measure. You can use this B to sort of have a fixed linear operator that sort of mixes through the noise modes a little bit more if you want. So in many cases that's reasonable from applications. Sigma will control the noise level and assume Q is trace class. Then you can actually prove quite easily that there is a mild solution, and this mild solution is just given by the usual convolution with the semigroup generated by A. A, again, think of A the Laplacian. So it's the usual heat semigroup in the standard reaction diffusion case. And you get the two convolution integrals, one deterministic one that you're used to, and then the stochastic convolution integral that you can make sense of. So let's assume that for the deterministic system, so for sigma equal to 0, U star, there's a trivial branch of solutions. So you should think of pitchfork or transcritical bifurcations that we want to tackle. Let's assume A, the operator, is basically given by an identity that's sort of shifted around, plus some more, like in curly A. And this curly A, so it's basically the standard example again would be the Laplacian. So you could think of that I would want to modify my A a little bit. And I would say, okay, I not take the semigroup that's generated by the Laplacian, but I want to shove into this semigroup also a piece that sometimes comes in, which is a sort of parametric shift of that semigroup, and that I will include into my operator A. And I will assume that my parameter V will actually shift the spectrum of this operator, which means I can actually generate a bifurcation point in the classical sort of, if you're an expert on this Krandor-Rabinowitz sense. So there will be a bifurcation point like a pitchfork or transcritical. And I assume that deterministic bifurcation happens at V is equal to 0. Now, what are the early warning signs for destabilization in this space-time stochastic setting? So let's do the same thing we did in the deterministic case. Let us assume we are allowed to linearize. I won't go through the proof. Of course, you have to prove that you are allowed to do that. So set the linearization here equal to 0. So assume that, set the f equal to 0. So assume we have shifted all the linear terms into the semigroup. And then you also assume that you are in the regime where the 0 solution that you are bifurcating off of is stable. Meaning you start with some initial value. Oh, there's a slight misprint. So u of 0 is of course the same as u0, yeah, with the lower index. And if you then send t is equal to infinity and you start sufficiently close near the 0 branch, then you can also get rid of the first term in the mild solution. So then if you are sort of assuming this means that locally near u star is equal to 0, near your deterministic branch, which you can think of basically now as the critical manifold again, near this critical manifold, you have to just deal with the stochastic convolution. You have to check how the stochastic convolution changes if you vary your parameter v. So how does the stochastic convolution change if I move my system towards the bifurcation point in the space-time setting? And indeed, you can do that. And now you have to go from the covariance matrix to the covariance operator. So I've sort of given the definition above here. You can take your stochastic process ut. You can define a covariance operator that just is sort of basically a composition of the semigroup, this operator B, and your given Q. And this operator, you can show that if you have a deterministically stable system, then indeed for this linear case, this operator has a long-term limit. It's the same like having a variance operator. If you are always in the stable case, then you get a long-term limit. Remember, currently we are varying the parameter quasi-adiabatically, so infinitely slowly. Then indeed I can take this limit t going to infinity and get a well-defined limiting operator u infinity. And this limiting operator u infinity, that solves again a Lyapunov type equation that I've written here. So, and I've projected it onto the basis functions of a Hilbert space. And indeed, you can show that this Lyapunov equation in infinite dimensions fully determines this operator u infinity, and that operator u infinity hopefully gives you the fluctuations when you approach the critical transition. Yeah. So remark, if you are not an expert on Lyapunov equations, you indeed see that this infinite dimensional Lyapunov equation is the same as sort of the finite dimensional matrix version. It's basically something like mx plus x m transpose plus p is equal to 0, where x is the unknown and m and p are given. So what we want is, if we have this covariance operator, we want to study it based upon varying V. So meaning based upon, if you make this covariance operator that you obtain from locally linearizing around your stable state for your deterministic PDE, you want to vary this with V, and then you want to check how it grows or changes if you approach the bifurcation point. Yeah? So here's the theorem that we proved with Karina-Gauda quite a while ago. So if you have a bounded domain and if you have a very nice eigenbasis for your operator, then indeed if you project onto this operator, that's the eigenbasis of Q, then you see that on this basis, then you have indeed a sort of very explicit expression for how this covariance operator acts. And if you assume the bifurcation point is at V is equal to 0, and if you assume you're in the standard Krenner-Rabinowitz case that there is an sort of eigenvalues lambda j and lambda k that go to 0, so you have part of the spectrum crossing, then indeed you see that this expression on the leading modes, when you project onto the leading modes that are associated to the eigenvalue that crosses to 0, so let's assume a standard Krenner-Rabinowitz single eigenvalue crossing, that this eigenvalue crossing, then you see this in a sort of associated eigenspace to this eigenvalue crossing, and you see that this covariance operator also blows up like 1 over V as V tends to 0. Again, that's the linearization, and there's a saturation effect very close to the bifurcation point if you would make V dynamic. Even better, we can even prove later on with Francesco Romano, if you had a more complicated spectrum, so not isolated eigenvalues that cross in a Krenner-Rabinowitz type fashion to give you a bifurcation point in infinite dimensions for the deterministic PDE that's, basically reducible via Lyapunov-Schmidt or center manifolds to a lower dimensional or finite dimensional case. But if you have a truly sort of essential spectrum, even for a truly essential spectrum or a spectrum that's continuous, you can actually see that you can still say that the covariance operator grows as you approach the bifurcation point. Although, so far we haven't been able to give a scaling law, but we are working on that. So this shows that you can generalize early warning signs even to SPDs. If you technically work quite hard, then you see that in the end, also for these cases, you can get and derive computable warning signs. So for branch points, as you would expect from the finite dimensional case, you get the scaling law 1 over V. Sort of that's generic. As long as all the modes are sufficiently mixing, you could even measure any mode. But if they are not mixing, then you have to find basically the spatial mode that you excite, meaning that you have to measure along that mode to figure out that there is the scaling law of the fluctuations. And now you're asking, well, what about dynamic V? Indeed, we are currently developing, there's a whole research program how to develop, even in the deterministic case, partial differential equations that are multi-scale in the sense of fast-slow systems. So you have also slow and fast variables. And then for the stochastic case, the first step of fast-slow SPDs was made in a paper with Manuel Gnan and Anne Pine in 2018. And of course, in the end, our final goal will be to give again like this SODE list, a comprehensive SPD multi-scale list where you have all the warning signs for all sorts of bifurcation points. So this is very nice. So let me also say, and I didn't have much time actually when I gave the talk live, so I will go over this also very quickly. Let me say that we can generalize also these ideas not only to stationary patterns like U stars equal to 0, but also to instationary patterns. You could look at warning signs for traveling waves. Let's look at the Fischer equation, for example. You know that the deterministic one has a traveling wave that's stable with minimal speed 2. And there's a front that connects 0 and 1. And this is a classical sort of front solution. And you indeed see that it's a typical propagation into an unstable state. So for this logistic nonlinearity, they would say in ecology, there would be propagation into the unstable state 0. And then you could check, okay, there's a front. But what about warning signs for changes in this front? So even this is possible. So let's suppose we have the Fischer equation with noise. You can choose various noises. You can choose something that's wide in time but completely independent of space. You could use space-time wide. You could use Q-trace class. You could use all sorts of noises, and you could all sorts of sort of choices of multiplicative noise usually, because normally you want to make U is equal to 0 invariant, because you are in this case in the Fischer equation mostly interested in applications where the solution stays non-negative. So to do this, you can actually put in something like G of U is equal to U, or square root of u, something that scales like this, or something like square root of u times 1 minus u. And there are various works that have dealt with sort of existence theory and studying the wave speed in the stochastic case when you have a stochastic Fischer wave. And I've cited a few papers here. This is a very active area per se. All right, so this is a numerical simulation for the case when you actually have only a noise that depends only upon time and not upon space. And you see here, if you start with something that's a little bit like a delta peak or a sort of approximate identity, something that's close to a delta peak, sort of a little peaky thing, then you know from the theory of the deterministic Fischer equation, two waves will propagate from that, one left moving, one right moving. You see this here for low noise on the left very clearly. But then if you increase the noise level, you indeed see that at some point there are cases where this wave can get absorbed into the absorbing state u is equal to 0. So there's actually propagation failure if the noise gets sufficiently large. So then you are like, okay, well, maybe, I should also think about warning signs for this. Yeah? Of course, in principle, you should model the noise as its own process and then study a coupled system. But let's just suppose you have this and you are now interested in the case when you have a pattern that's in space and time, that's moving in space and time, and for a warning sign for a transition that's not easily identifiable as a local bifurcation point, which this clearly isn't, because it's sort of a more global effect where you get absorbed into u is equal to 0. And if you wanted to write it as a bifurcation problem, you definitely had to do some rewriting before you can identify it as one. So then the question is, are there warning signs? And indeed, if you look at the single point observer statistics over a finite time span, so the mean and then the fluctuations around the mean, you see that if you increase the noise level, there's actually a change in the mean, a change in the mean speed, but also a change in the fluctuations around the mean. And you see, if I increase the noise level, it seems to be that the fluctuations sort of get squashed in this simulation if I average over many sample paths. And then you are like, okay, maybe I can use the change in the fluctuations as a warning sign for the propagation failure of this wave. So at least there's hope. There's no full theory, but at least there's hope that even for more complex patterns, there's heterogeneity or non-uniformity in the spatial stochastic statistics. That means even for those patterns, you could hope that there are warning signs, and this example of this traveling wave demonstrates that quite clearly, that there is this heterogeneity. Yeah? So as I said, I won't go into detail in this case a lot, so since I didn't have much time either when I gave the talk live to do that. Alright, so now a little bit on extensions for warning signs for network dynamics. So we covered stochastic ODEs, we covered stochastic PDEs locally, and we are still working on refining that theory. We have seen that for stochastic PDEs and patterns, there's at least some hope to get warning signs. But what about network dynamical systems? What can we say about these? Can we find warning signs that are sort of related to network properties? Alright. So here's an example of a network dynamical system. So take an epidemic model, this is the one I like quite a lot, from Thilo Gross from 2006 and collaborators, which is a standard SIS model on a network. So there's an epidemic model with infected and susceptibles. There's a certain rate at which people can get infected along a link when they are in contact with an infected person, which is beta. And then there's a certain recovery rate, R, how people get healthy again, because it's an SIS model. They basically go back into susceptible after they have been infected. And there's a recovery rate R, and the additional sort of twist of this model that Thilo developed in 2006 is that there's rewiring, meaning if you are connected to somebody who's infected, then there's basically this social distancing effect that you say, well, I don't want to sort of get in touch with that person, and you rewire your friendship or social contact link to a person who is healthy, and sort of there's a certain rewiring rate at which people do this, at which they're trying to, sort of avoid people who are sick for a while, and then make sure that they sort of actually connect to people who are healthy. So this model obviously is a fully adaptive or co-evolutionary network, meaning there's dynamics on the nodes, but also dynamics of the topology on the network. So it's fully changing, it's fully coupled. And if you look at this, you can actually write ODEs, low-dimensional evolution equations. If you do something that's quite common in epidemiology, you look at the moments, so the infected density, the density of II links, the density of SS links, the density of susceptibles, the density of susceptibles and infected by conservation law of nodes and conservation law of links. you can reduce the 5 equations to actually 3 equations. And then you have an infinite chain of moment equations because the second order moments depend upon the third order moments. So these II densities depend upon ISI, SSI, etc. and so forth. And you can truncate that by doing a sort of formal pair approximation. Yeah, you can say I approximate triplets by doublets. This is this typical pair approximation. And then you get a closed system of ODEs. So then you're like, okay, I have this closed system of ODEs. Then for this epidemic model, I should be able to apply my early warning sign theory that I developed for stochastic ODEs indeed. So if you assume that there is some additive noise, for example, and some parametric drift, so assume the beta, the infectivity is drifting, for example, it's slowly increasing. Yeah, so you add noise and the parameter drift to this, model. Yeah, that's a formal addition, of course. Yeah, and you do some reflection of the noise to make sure that you actually keep the invariance of the positive quadrant, so to make sure that you actually have, non-negative infected numbers and so on. If you do that, and if you adjust the Brownian motions in a suitable way, then indeed you see that you get a system of 4 SODEs. And to this system of 4 SODEs, you can indeed apply early warning sign theory. The deterministic bifurcation diagram is given down here. You have a transcritical bifurcation where basically I0 is equal to 1, where you have a sort of point where you have a critical transition that's possible due to the adaptivity for certain values of W. So you basically make a big jump if you jump over the epidemic threshold. And then there's a second transition when you decrease actually the infectivity again. At some point you jump from the epidemic states from a large epidemic back to sort of very close to where there's no epidemic. So there's 2 transitions that are visible in this model. And if you do that with noise, then you can indeed find that the early warning signs by the results that I had mentioned in the beginning. So for the transcritical bifurcation, there's a warning sign that goes like beta minus beta, that where the transcritical point is, to the -1. And you can indeed measure this, for example, very well in the variance of the link density. So you see this very pronounced in the variance of the link density, and then you can use this as a warning sign. But this is sort of reducing this network dynamical problem via moments to a sort of standard ODE problem, and then you basically apply all the SODE machinery for warning signs to figure out what's going on. But then we were wondering, well, we are actually in a network problem, so we have all this sort of great network science machinery. Can we use that actually? So the idea was, what can we do with network measures as warning signs? So let us focus on the upper branch. So let us focus, of course, we could use standard SODE theory and check whether we can find warning signs for the fold. But we could also think, well, the network is changing. Maybe I can use network quantities to figure out how far I am from the bifurcation point if I decrease my beta. The bifurcation point is where the dashed vertical line is. And you see here a scaling law for the effective branching ratio that is defined as this ratio of these moments. And then you're like, well, there's a scaling law of this, but the scaling law indeed barrels through this bifurcation point and continues on. And the scaling law is relative to beta is equal to 0. So it's actually not a warning sign despite the scaling law. So, okay, then we were thinking, what about other network measures? So what about the clustering coefficient? Yeah. So the clustering coefficient, you see here, indeed, if you decrease the beta, the clustering coefficient has a very nice little peak. And this nice little peak occurs a little bit before the actual bifurcation point. So this could be used in this model as an excellent local early warning sign. So if you measured local clustering, and if you saw some changes in the clustering, you could say, aha, maybe we are now close to changing back from the epidemic sort of state or the endemic state to the state where you're close to no epidemic. And then you're like, aha, now I've sort of found the principle. I have a fully adaptive or co-evolutionary network, and I vary my parameter, and upon variation of my parameter, I checked what sort of network quantities change in time when I go towards the bifurcation point. And then you check, okay, effective branching ratio doesn't work, clustering coefficient does, the link density, of course, does, because that's what you expected, because you know that already. The harmonic mean distance doesn't work, associativity does work, variance of the degree distribution doesn't seem to work, and the eigenvalue gap of the Laplacian defined on this network does work, and so on. So, and this we did together with Leonard Horstmeier and Stefan Turner, and published this a few years ago. So you can indeed sort of start to classify, can you use topological warning signs or changes in the topology as warning signs for these critical transitions? And yeah, so this is still an area where there's some math to be done, because we have to classify and try to find something that's sort of, similar to the ODE classification. This probably does exist, but it's of course much more complicated because you're playing with these additional sort of high dimensional systems, and you're playing with sort of observables from on this high dimensional system, which are much more difficult to control in comparison to you already having a very well controlled observable in a low dimensional ODE that's given to you. You have to basically do an additional step to figure out what these observables are doing. So, but it shows you in principle this critical transition in early warning sign theory can be generalized quite systematically to networks, and in particular I think adaptive and co-evolutionary networks are an excellent playground for this. Alright, so again this can be extended. So we showed that indeed you can do this in sort of epileptic seizure models, and there you can find warning signs if you measure sort of certain electrodes in ECOG data, 45 electrodes. We did this together with Chris Meisel. Then you can try to do this for Twitter events and social science. This turns out to be very difficult to predict. We weren't very successful. It's probably due to the high sort of forcing and heterogeneity of social systems that makes it very difficult. You can do this in low-dimensional systems, so in neurons, via precise scaling laws and data. And we also develop warning signs for so-called saddle-type transitions, where there's no loss of normal hyperbolicity, and where we even applied this to measles data, where we had sort of heteroclinic type outbreaks, and you can figure out how close you are away from this heteroclinic type loop. So there are also warning signs for cases when you have sort of more global structures. Yeah? So there's lots of stuff. There still needs to be done. This is just a few papers that I'd worked on, but again, I could cite thousands of papers that try to sort of directly or indirectly really figure out what these critical transitions in more complex systems are and how to tackle them. So now the last topic I want to briefly spend maybe 5 to 10 minutes on, because that's roughly what I had also in the live setting, is this question of resilience. So far we have mostly dealt with local transition points and a little with global ones. But for global sort of changes in the structure of our dynamical system, particularly in ecology, people have been interested in how can you measure this actually? What are measures for more global stability? And this brought up this notion of, what is a resilient system? How can you actually deal with resilience? And what is this really? So there's a long conceptual history, there's many papers, for example, of May and Holling, that popularized this concept in ecology. If you go into the math literature, remember the sort of rebranding thing, that there is actually a paper in 1959 on structural stability, and there's probably lots of earlier papers that deal with the idea of what can we do for dynamics if we are not looking locally, but we are trying to measure how it is stable more globally, and how do we attach a number to this. So most papers do not define resilience, and there are even some papers that argue against even defining that concept. I'm sort of not in line with these papers. I would say we need to define it, and we need to be sharp about it, and we need to be quantitative about it, and we need to give definitions, and we need to do comparison of definitions, and we need to have something to rely upon, because otherwise we will just move in circles. And this can happen, and I will at the end of the talk sort of give you a little bit of a sort of explanation why I think this is necessary. If you don't define it, you are likely to move in circles here and you won't get anywhere. And if you look at the resilience literature to a certain extent, quantitatively from really mathematically pinning it down, it hasn't really moved very far since the 1970s. So then we said, well, we need to mathematically pinpoint resilience as a concept, and not only with one concept, we need to give a comparison of all the concepts that have been proposed. And we have actually write down all the definitions, put them next to each other, mathematically make them completely precise, make them very general to apply for very general systems, particularly those where you, for example, have slowly varying parameters or non-autonomous dependence. And then we wrote this paper with Hanna Krakowska and Jacopo Longo, which I think is very nice, where we go through all these concepts and at least give definitions for all these resilience concepts. All right, so here, this is sort of the main table in the beginning of the paper. So one could roughly classify it into sort of two types of resilience. One is sort of how long will it take for a system that suffers a perturbation more globally to readjust? And the second one, you could call ecological resilience maybe which are the features of the perturbation that the system can sort of endeavor or is actually sort of endure to still return to its original state. And we went through the literature and we picked up all these different sort of ideas how to define resilience, and then we classified it. So these numbers that are next to the actual sort of label of that resilience indicator point you to the section in the paper, and it tells you, for example, if you wanted to know what really is stochastic invariability, you go to section 3.8 and there is the precise definition of this indicator. Or if you wanted to know what is like intensity of attraction, then you went to section 5.6 in the paper and there would be a discussion mathematically how to define intensity of attraction and how it sort of, can be viewed and what are the basic mathematical properties. Also, then the perturbations can be different, of course. So, and then we classified it also according to perturbations. So you could perturb in the space of initial conditions, you could perturb in sort of time-dependent settings like forcing, or you could perturb in the space of parameters, or well, structurally speaking, you could also say I perturb in the entire sort of structural class of vector fields of dynamical systems. And I want to compute a global stability metric. Of course, as you can see from this table, there is no unique definition of this, obviously, right? Sort of locally, like always in dynamical systems, you can hope to give one or two reasonable definitions, but once you go more global, then usually many definitions pop up that are reasonable. This is well known again, for example, from attractor theory, there are many reasonable global definitions of what an attractor should be, but locally, if you are actually in an arbitrary small neighborhood around a point, then attractors become point attractors, there's only one reasonable notion, and then also only basically one reasonable notion of stability, or say two, namely Lyapunov and asymptotic stability. But if you are actually more global, then all these different notions of stability pop up that what could be summarized under the notion of resilience. So what did we do? I will go through this not in full detail because it's the end of the talk and I also didn't have much time when I was in Leiden to talk through this, to keep the talk a little bit to its sort of original presentation. So what we did is we really mathematically defined things precisely for a very general system. So you go through a system, you look at an attractor, this could even be non-autonomous in this case, this system, and then you look at, okay, what is the return time to this attractor? And the return time can be defined via this sort of formula here. This alpha hat is defined via this infimum, where actually this y is the Funda matrix of the linearization around a certain solution. And then you can actually show that, okay, there's a characteristic return time to a given solution. And then this is the sort of smallest return time that you could have. Well, or the largest in this case, the largest return time because you're actually taking the inverse. So the largest return time that you could have to return to your attractor. And this is even written for fully non-autonomous systems. You could look at the mean return time. You could look at the maximal return time. You could look all sorts of stuff. How long does it take after an initial perturbation to go back to my attractor as long as I'm starting with my dynamical system from the basin of attraction. And then, well, if you do that, you write down mathematically very precisely what these objects are. Like what is a maximal return time, what is a mean return time, and you get formulas that you could have a look at. You could do this with a distance to threshold. You could look at a set and say, what's the distance to threshold? You have an attractor. And the question is, how far are you actually away to a threshold where you could jump away from this attractor? So basically from a basin boundary. And then you could say, all right, for a general dynamical system with a continuous flow, how far are you away? And then you figure out, okay, it's the infimum basically to the boundary and then to the basin of attraction. And this infimum then gives you a measure of global stability because it gives you a distance measure to the basin boundary. You could figure out what's the volume of the basin. That gives you, basin volume. In some sense, it's a measure of global stability or resilience, and so on and so forth. I won't go through this in detail. This is a very complicated definition. You could look through a control theoretic notion of looking at all sorts of, forcing type perturbation or control type perturbations, and then you can define which types of these perturbations you can allow. And that gives you a notion of intensity of attraction. So what sort of controls can you resist and still sort of go back to the attractor? and then there's resistance, and so on. There's lots of measures, and we have written, as you can see here, as I said, I won't go through all the definitions because I didn't manage to do that in the live talk either. But in the paper, you can go through all of these definitions, and it tells you, you get all these measures. Okay, so what can you do with this? Elasticity, you define that, and so on. You can actually compare. So you take your dynamical system, you have all these different measures that are numbers that tell you how resilient or how globally stable your system is. For example, return time, which is more the sort of classical, sort of something that's related to local asymptotic or Lyapunov stability. Then you have the distance to threshold, intensity of attraction. Remember that this was the controls. Then you had resistance and elasticity and so on. And you compare all these measures. These are only like 6 here that I have given here. And let's take a simple Lie effect ecological system. And then let's take several parameter values for the system. So basically several types of species that are possible. And that gives you several types of possible dynamics of this one-dimensional system. And then you, for these 5 species, are interested in, okay, what's actually the resilience measure? So how resilient is the stable state that you see for the species as the stable existence state of a certain population size? How resilient is that state for these 5 different sort of very simple population species models? Okay, and then if you look at it, and on the left you sort of have plotted a few of these indicators here, and then high resilience is sort of in dark blue and low resilience is in white or light blue. Then you see they vary very broadly. You see that you can actually sort of vary the parameters of your system, and then there's high resilience for one indicator that has a much lower value on another species. For example, if you take this inverse return time, then for species 1 it's quite small, but for species 5 it's actually quite large. But for example, elasticity and intensity of attraction, they behave differently. They are the largest for another type of species, but much smaller for other species. So this shows you quite clearly that you could argue ad infinitum. You could say, if I don't really define resilience, then you could say, well, maybe this species is more resilient, or well, maybe this species is more resilient, or the most resilient ones. Because if you only looked, for example, at intensity of attraction, you would say, well, species 3 is the most resilient. But if you only looked at mean return time, or at the inverse return time, you would say, well, species 5 is the most resilient. So this shows you that if you don't define stuff properly, then indeed you could argue sort of and wave your hands ad infinitum, but here you quite clearly can start combining things, and you see that these indicators are sort of measure disjoint things in a way, and they give you a different type of resilience. So meaning that there's not only one notion, but there are many notions, and they need to be mathematically compared, because otherwise it just becomes sort of the wild, wild west without any laws. And that's how the resilience literature to a certain sort of degree actually reads like. It's very difficult to read and very difficult to follow because you cannot rely on a fixed set of definitions. And now we have given at least the first attempt at this fixed set of definitions. Alright, so now I'm finished with my talk. So first of all, brief summary. Let me highlight again, critical transitions are bifurcation phenomena, even though if they're not visible as such in the beginning, they just are. Either they are local or they are global, or they're sort of related to a global solution that's bifurcating, and so on and so forth. Of course, there are these saddle effects, these saddle type phenomena. So you could have, of course, sort of have saddle induced critical transitions. These are not bifurcation phenomena, but this is sort of the most of them are actually bifurcation phenomena. Then you have the SODEs. You have a classification for warning signs, which is basically almost done. SPDE warning sign classification is in progress. We are very far already. We have done quite a good job, I think, in lifting the theory from purely time dependent to space-time. For networks, we gave them a sort of first classification and have given the idea that adaptive and co-evolutionary networks, you could draft in all these sort of additional topological warning signs. And for global resilience indicators, so what does it actually mean for a system to be globally resilient? So we are far away from what happens when the resilience drops. And can we find warning signs for a drop in resilience? So we first have to define what we mean by global resilience. We have given a very first coherent layout of this. And for all of the details that I didn't have time for, unfortunately, because my time is actually more than up. I've talked a few minutes more than I actually was able to talk live because I couldn't sort of restrict myself enough in this setting of re-recording the talk. But if you want to look more at my papers and the work of my group, and then you please look at this website that tries to be easy to remember by this name, multiscale.systems. And there's, of course, more talks on the same YouTube channel where you're watching this. So please have a browse around and see if you're interested in dynamical systems, whether there is something that you're interested in. And then I would like to thank you very much for your attention.